Good morning to all the participants to this session after tea today. Today I will discuss the principle of physical similarity and dimensional analysis. Now at the outset I must tell the implication of the physical similarity and the dimensional analysis. Implication means that what is the need of this. So first of all we try to understand in this way that the practical problems or the engineering problems are complicated in nature, and because of these reasons the solution to most of the practical problems are given or derived by the experiments. This is because even if we do the theories, and in spite of many advanced theories, it has been found that sometimes it is difficult to take care of all the phenomena that happen in reality, and therefore at some point of time in our theoretical analysis we have to depend on empirical information, just like wall function in a turbulent closure model. Moreover, even if the theories are developed, they have to be calibrated or corroborated by the experiments. Because of this, the solution to the practical problems are derived mostly from experiments, which means that if we want to design a system in practice, we have to do the experiments to find out what should be the operating conditions of the system and the influence of the operating conditions on its performance parameters, based on which we design the system in practice. So these experiments are done in the laboratory. Now the main thing comes into consideration here that we cannot make the identical situations of this system in practice for our experiments in laboratory. We cannot. For example, if we want to predict the nature of the surface waves created in a big river or the nature of the spillways of a dam, we cannot create a river or a dam that is there existing in the practice in our laboratory. For example, if we want to find out the pressure distribution around an aerofoil of an aircraft, okay, we cannot have an aerofoil of that dimensions which is there exactly in the aircraft. Moreover, we cannot make or create the situations that exist at a high altitude, that means that pressure and temperature in the laboratory. Another example I am giving, if we want to predict the system performance like the flow of water through a pipeline for supplying water in a city, if we have to do experiments in our laboratory, we cannot, we are unable to make the pipes of such large diameter. Sometimes it is difficult to provide in certain cases the fluid which are actually used in practice. So therefore we see that laboratory experiments are done always under altered conditions that actually exist in practice with respect to fluid mechanical parameters like geometry, the fluid property, pressure, temperature, velocity of flow and all these things. Now a big question comes in this regard, that then how can we predict the results from the laboratory experiments which are done in a different set of conditions that happen in the practice? How can we predict or interpolate the results from laboratory experiments to the system in practice, because of the fact that two are not in the same set of conditions? How can we do it? So there must be some principle based on which this interpolation is possible, so that we can predict the results from the laboratory experiments under altered set of conditions to that of the actual system in practice. This is number one query. Number 2 query comes in this regard is that, okay, now we accept some principle is there which will allow us to predict the performance done in the laboratory or the experiments done in the laboratory under altered set of conditions to predict the performance of this system in practice. We accept it. Now second thing comes that if a performance parameter depends on a large number of independent controlling input parameters, then a large number of experiments have to be done. For an example, I tell you that in case of a pipe flow, if the pressure drop over a given length is to be found out as a function of controlling parameters, we see that it depends upon the diameter of the pipe, it depends upon the rate of flow of fluid, it depends upon the fluid property like density and viscosity. So if we have to predict this performance with respect to these operating parameters, we have to vary the diameter and see its effect, diameter of the pipe. We have to vary the velocity and see its effect. We have to vary the density of the fluid for a given viscosity, we have to find its effect. Similarly, the viscosity has to be varied and find the effect. So is it possible by any chance in this case to vary one parameter and to predict the performance or the relationship influence of other parameters on the performance parameter? That means if we simply vary the velocity of flow, can we predict the influence of diameter? Can we predict the influence of density, influence of viscosity, so that we can reduce the number of experiments? So therefore it is clear, because of this economic advantage, because of the time saving, because of the space requirement, it is not possible in the laboratory to do the experiments under the identical conditions to that actually exist in practice for the actual system, and at the same time we want to reduce the number of experiments, not varying all the controlling parameters, but varying a few parameters, and from that try to extrapolate the influence of other parameters. The thing which makes it possible is the principle of similarity. Rather, I should tell in this way, a clue to the answer of these two problems, of these two queries, is given by what is known as principle of physical similarity. Then with this in the background, we should see what this is, the principle of similarity. That means if the principle of similarity exists, then we can compare the results or we can predict the performance of a system from the laboratory results under altered set of condition, and at the same time by varying a very few parameters in the experiment, we can predict the influence of other parameters. Then what is this principle that allow us to do so? Physical similarity. Now I will discuss. Now the physical similarity, principles of physical similarity. Now come to the actual problem, physical similarity. Now physical similarity, first and foremost requirement for the physical similarity of a process, two process or two systems, is that the physics of the problem has to be same. This is very important, and I don't know how many books write these things, that physics of the problem or the system, physics of the problem of the system has to be same. That means we has to be same, that we can explore the similarity between two systems or two problems provided they are defined by the same physics. That means physics of the problem has to be same between the two systems between which the similarity is being sought. An example, a fully developed flow through a pipeline or through a pipe cannot be made similar to the flow or the flow of fluid through an open channel, because the physics of the two problem is different. Flow through a pipe or a closed conduit is governed by pressure force, viscous force and inertia force, whereas in a flow through an open channel, gravity force is very important. Gravity force is very important, there is a free surface, so the entire physics is different. Another example I am giving, which looks very similar but the physics is different. If you think of a flow of fluid through a vertical pipe of big diameter and flow of fluid through a very small pipe, the difference is that though they look almost similar, the physics is different. In a bigger vertical pipe, the flow is being governed by gravity force, pressure force, and the pressure force is taken by the gravity in terms of piezometric pressure. So, therefore, I will tell pressure force, viscous force and inertia forces. While in a small tube, the flow of through a small tube, the capillary force is very much predominant. So, therefore, when the physics changes, we cannot seek or we cannot explore the principle of similarity. So, primary and fundamental requirement for physical similarity between two systems or two problems, that their physics, that the physics of the problem has to be same. So, then I define which is principle of similarity. If this fundamental requirement is made, then it is defined like that. You just listen to me, then I will write, you will understand that the two systems defined by the same physics is said to be physically similar with respect to some physical quantities if the ratio of the magnitudes of that specified physical quantity between the two systems is same everywhere. Clear? That means two systems having the same physics, because without same physics we cannot seek for this physical similarity. The physical similarity of the system means with respect to a particular physical parameter or physical quantity. If we tell that these two systems are similar with respect to a physical quantity, then the ratio of the magnitudes of that physical quantity between the two systems should be same everywhere. Now, when this physical quantity is geometrical dimensions, it is known as, when the physical quantity is geometrical dimension, then it is known as geometrical similarity. There are three such physical quantity: geometrical similarity, because a fluid flow, as you have already seen now after so many courses, is governed by the fluid kinematics and dynamics. So, ultimately geometry of the system, fluid motion and the force, these three are the important things. So, therefore, we only discuss this because these three physical quantities come into picture. When the physical quantity concerned is the motion, okay, then it is known as, or the velocity, it is known as kinematic similarity. Okay, then it is known as kinematic similarity. And when this concerns force, the physical quantity is force, then it is known as dynamic similarity. So, according to the definition just I told you, dynamic similarity. So, therefore, according to the general definition for geometric similarity, the corresponding geometrical dimensions between the two systems or problems should be same everywhere. Similarly, for kinematic similarity, the motion, that means the magnitude, ratio of the magnitudes of the velocities at the corresponding point should be similar between the problem and the system. And similarly, for dynamic similarity, it is the ratio of the forces between the system, corresponding forces between the two systems should be same at everywhere. So, let us go into little detail of this geometrical similarity, kinematic similarity and dynamic similarity. But before that, I tell you, when these three similarities are maintained, that means when the three similarities exist between the two systems defined by the same physics, then we call the two systems are in physical similar conditions. The entire physical similarity exists between the two systems. That means again the two systems have to be defined by the same physics, and all the three similarity, geometric similarity, kinematic similarity and the dynamic similarity have to be maintained. Okay. Now, let us go one by one. The geometric similarity is the most simple similarity which is understood very well since our childhood. We know the geometric similarity between two systems or two objects means their corresponding dimensions are in the fixed ratio and their shape, that means it represents the shape of the body, same shape. Now I can show you a simple figure for the geometrical similarity. It is very simple. You see the two cylindrical objects are geometrically similar. Here height and its diameter are the two characteristic dimensions. Here you see both are divided by 2. That means this is known as the scale factor. The ratio is known as the scale factor. Similarly for the parallelepiped, the two parallelepiped are there. Their corresponding dimensions are differing by a ratio, are varying by a ratio half in the two case or 2 any way we tell. Similarly you say a triangular prism. So therefore you see this represents a very simple thing which we know since our childhood is a geometrical similarity, and here the scale factor you see for all the figures is either half or 2. That means the corresponding dimensions are reduced by half or increased by 2 between the two systems. So this is the example of geometrical similarity. Now I tell you about the kinematic similarity. Now kinematic similarity is the similarity of motions, which means that the motions are similar. Now in general you see the motion is described by what? Distance by time. So therefore distance is related to the length scale. That means when the geometrical similarity is there, so the lengths will be similar. That means the lengths in the two systems are in a fixed ratio. So therefore to achieve the kinematic similarity, the time duration for any particle to reach from one station to other station, one point to other point should be in a fixed proportion, okay, between the two systems. So therefore kinematic similarity, geometrical similarity is a corollary, or geometrical similarity is not a corollary, sorry, is a prerequisite to that. It is a necessary condition that geometrical similarity has to be there for kinematic similarity. Now for kinematic similarity, velocities at the corresponding points of the two systems have to bear with in the same ratio. That means if I define for example the axial, this velocity u, v and w. Now for the system, two system, what will be there? So u for system 1 to u for system 2 must be equal to v for system 1, two systems between which I seek this system 2. Similarly for that w for system 1 in a 3-dimensional case, I just example is giving, that is the kinematic similarity, that means at the corresponding point. That means the ratio of the velocities, corresponding velocities will be same, or you can write u by system 1 divided by v system 1, u system 2 divided by v system 2, and this has to be valid at corresponding points, the velocity components u, v, w, for example u, v, w in a Cartesian coordinate. Now corresponding point you have to know, that is geometrically corresponding point. What is that? Already we have seen that the geometry. Now let us consider this way, then you can understand at the corresponding point. Let us consider a channel flow, a small channel, and let us consider here a big channel, flow through a small channel, flow through a big channel. And these channels flow if we maintain the geometrical similarity by maintaining the h by l same. Now what is the corresponding point? Now this is wall, this is wall. Let us consider this as h1, the height for this channel, and height for this channel is h2, and we consider that h2 is greater than h1. Now what is the wall location? System wall ready y coordinate for wall for system 1 is h1. The wall for system 2, wall means the y coordinate of wall, I am not writing everything, is h2. So the y coordinate is varying for this wall from system 1 to system 2, where the no slip condition prevails. If this channel wall is fixed, then the velocity is 0. But if we define a dimensionless coordinate y star as y by h, then what is, this is y for wall, y is equal to h. Rather you write, it will be better, y is equal to h. But while y star for both the system will be 1, because in this case it will be h1, it will be h corresponding h. If we define by the corresponding h, if we define here all the y coordinates are normalized with corresponding to h. So here y star will be y by h1, h1 by h11. Here also y is equal to h2, h2 by h2 will be 1. So y star will be 1. Similarly, if we take a point at the middle where y coordinate is what? H by 2, half of the width, but then y star will be half, because it is already normalized with it is normalized with h. That means these are the corresponding points, geometrically similar points. So therefore the ratios of the velocities will be same at the corresponding points to maintain the kinematic similarity. Okay, I think it is understood well. So this is kinematic similarity. Now you see, since the kinematic similarity relates the velocity ratios and velocities are given now by this streamlines, if you consider the streamlines, the velocity direction is given by the streamlines. So velocity not only by the magnitude but also by the direction is a vector, velocity is a vector. So therefore the streamlines have to be identical for kinematic similarity to be obtained. And as you know that an impermeable solid boundary represents a streamline because there is no flow across the boundary. So therefore for a kinematic similarity to be maintained, the boundary being one of the streamlines has to be similar. Again you see that geometrical similarity is a prerequisite or necessary condition for the kinematic similarity. Okay. Next we will come to dynamic similarity to understand. Kinematic similarity is simple to understand. Dynamic similarity relates with the force. Again I say the similar way that between the two systems at the corresponding points or the geometrically similar points, the ratio of different forces is same. Ratio of different forces govern the process is same. For example, if the fluid flow is governed by viscous force and inertia force, then the ratio of viscous force by inertia force at the geometrically similar point should be same. That means dynamic similarity pertains to the forces, and the ratio of the forces at the corresponding points, forces means forces governing the flow at the corresponding points has to be same. So if there are 5 forces governing the flow, the ratio between one another have to be same for the corresponding points between the two systems. That is the dynamic similarity. So therefore dynamic similarity is the similarity of the force. Now what are the forces acting on a fluid flow? If we take in general, the forces acting in a fluid flow are inertia forces. Inertia forces we know. Inertia forces is the negative of the resultant forces caused by other forces. So therefore I write first the inertia forces. Let us consider this as Fi. Then some common forces acting, another is the viscous force. Viscous force. Another is the viscous force. Let the forces to be written which govern the fluid flow in general, usually viscous force. Another is the pressure force. For our understanding, I am writing usually the forces which are governing a fluid flow in general, which govern the fluid flow in general. Viscous force, pressure force. Another is the gravity force. Gravity force. Let us consider the gravity force equals to Fg. There may be other forces, surface tension force. You have already seen that surface tension force. Surface tension force. Surface tension force. Let us define this by Ft. There may be elastic force which comes in case of compressible fluid because of elasticity, bulk modulus of elasticity, elastic force, which I write as Fe. So these are in general the forces. There are number of forces. This is general means I tell not in that way it is they are the only forces. It is usually just we can write or list some forces which govern the fluid flow. And a fluid flow phenomena governed by all these forces can be written like that, that sum of all these forces, pressure force, the gravity force, surface tension force, compressible elastic force should be 0. This is the D'Alembert's principle, that sum of all the forces equal to the resultant force, negative of which is the inertia force, and algebraic sum of all this is 0. Now therefore, if two systems governed by all the forces have to be dynamically similar, then the ratios between any two forces between the two systems at their corresponding points have to be same. That is the condition of the dynamic similarity. So next what we like to do, we like to find out what is the order of magnitude of all these forces. Let us do that in terms of the characteristic dimensions of the problem. Characteristic dimensions means we want to express these forces in terms of its representative magnitudes or order of magnitudes by, not in terms, by its order of magnitude or by its representative magnitude in terms of the characteristic dimensions of the problem, mainly the characteristic length of the problem or system, any characteristic length over which changes take place or characteristic changes take place, the velocity, characteristic velocity. Now we will not write any C, this L means characteristic length, V means the velocity, and other properties which come into picture like rho, mu, surface tension coefficient, bulk modulus of elasticity, all these things. Let us do that. Now first let us find out what is this magnitude of inertial force. This is proportional to, or you can write, or proportional to what? Mass into acceleration. Now mass is proportional to density into the characteristic length q. This is proportional. We can write in terms of order of magnitude also. That means this can be written sometimes in this way also. The order, this is another way of writing. The order of magnitude is equal to the order of rho L cube, that is this rho L cube, or you can write in terms of proportionality. Either way it can be represented. Mathematical expression represents either way. Order is equal to this or it is proportional to this. Mass into acceleration. Now acceleration is proportional to velocity and the time. Time is proportional to again characteristic length by velocity. That means this becomes rho L square V square. We can write the same way. It is the same thing expression. This is expressed in terms of order. That means this is the order of rho. So therefore, in terms of the characteristic length of a system or a problem and characteristic velocity and density of the fluid, the order of the inertia force or the inertia force, representative magnitude of the inertia force becomes rho L square V square, rho L square V square. Clear? Now let us find out viscous force. So what is this viscous force? The order of magnitude or the representative magnitude of viscous force, and the viscous force is proportional to what? Viscous force is viscous stress into area. Now you remember viscous stress is defined as mu times the velocity gradient. Simple case it is mu del u del y. In a 2-dimensional case, 3-dimensional case, in a 2-dimensional plane mu del v del x plus del u del y, that means the rate of shear strain or rate of angular strain, which is nothing but the velocity gradient. Whether that is one term or two terms is not important here. Here important is that mu times the velocity gradient, and velocity gradient is proportional to velocity, characteristic velocity to the characteristic length. Velocity gradient is proportional to this. That means the order of velocity gradient is the velocity divided by the length, characteristic velocity divided by the characteristic length. So velocity gradient can be expressed by this representative magnitude wise times the area. This is the viscous stress area. So this becomes equal to, that means this equals to mu v into L. Well, now we can write another force, that is, for example, the pressure force. Pressure force, how do you get it? Pressure force is equal to the, now here usually the convention which we follow, pressure force is expressed or representative magnitude in terms of a representative pressure drop. In a fluid flow problem, this pressure drop is taken as a representative pressure drop, like characteristic length, characteristic velocity, we take a characteristic pressure drop. Sometimes this is taken in terms of the static pressure at the wall and that of the free stream in case of external flow. So, delta P into the area L square. Let us consider the gravity force. The gravity force. Gravity force, the representative magnitude is again the mass into acceleration due to gravity, rho L cube into G. Surface tension force. Surface tension force, as you know, the representative magnitude is surface tension coefficient into characteristic length, because surface tension force acts along the periphery of the interface, along the length of the interface. So, surface tension coefficient is defined as the surface tension force divided by the length. So, surface tension force is sigma L. Similarly, we can express the compressibility force also, the representative magnitude, that is proportional to what? The pressure difference due to the change in this the pressure difference due to its elastic nature, which is manifested to its bulk modulus of elasticity. That means the pressure change because of the this is the change in the volume because of the change in the pressure, that depends upon this because of the elastic nature. So, therefore, the change in pressure in this case is proportional to the modulus of elasticity times the L square. Here modulus of elasticity represents the is proportional to the change in pressure, because we have to find out the force, the change in volume because of the change in pressure. So, therefore, that change in pressure is proportional to elasticity. When we represent that change in pressure by elasticity, coefficient of elasticity, and then L square, this becomes the elastic force, not this pressure force. There is a difference between this pressure change and this pressure change is different. This is manifested by the property, that is bulk modulus of elasticity. So, this is the representative magnitude of the elastic force. Now, with this type of representative magnitude, if we now try to find out the ratios, the dynamic similarity, the ratios have to be same. Now, if we make the ratios of each and every one, let us consider we find out the ratio of all forces with respect to inertia forces. If we make the ratio with respect to inertia forces, then viscous by inertia force, if you make the ratio as we have done, we will get mu by rho VL. So, this is a dimensionless group which represents the ratio of viscous to inertia force, and the reciprocal of this, rather Fi by Fv, the reciprocal of this is equal to or proportional to rather rho VL by mu. This is known as Reynolds number, that already you know, Reynolds number. Similarly, if we take the ratio of the gravity force to the inertia force, magnitude ratios, it is proportional to, if you see the gravity force is G. So, what is that? Gravity force is rho L cube G and inertia force is rho L square V square, that means G L by V square. This is the representative magnitude of the ratio of gravity to inertia force, and the square root of this, that means G L to the power half by V, this is by convention, is known as, that means this is also the representative magnitude of this, but with the square root, this is known as Froude number. These are by definition, and all these numbers are based on the scientists Reynolds, Froude. Similarly, if we take the, for example, the surface tension force divided by the inertia force, the ratio of this representative magnitude, that is proportional to sigma L divided by rho L square V square. That means what is that? That becomes equal to rho V square L, and that is known as Weber number. And this way we will get such dimensionless number if we get the elastic force due to compressibility to this, we will get elastic force E L square and rho V square L square, so it is rho V square, and this is known as Cauchy number. These are all the number known. And another thing is the square root of this, that means root over E by rho and reciprocal of this, and if you make a square root, this becomes root over E by rho, and that is known as Mach number, a reciprocal and then square root. So therefore you see that all these numbers are known to you today. Now this represents the magnitude ratio of the two forces. So therefore if a fluid flow, there are other things I have not derived, that pressure force by inertia force. That means if a problem governed by the viscous force by inertia force, then this grouping, that Reynolds number has to be same at corresponding point. Similarly for gravity and inertia, this grouping has to be same, that Froude number has to be same. Similarly if a flow problem is governed by surface tension and inertia force, this has to be same. And if it is governed by all the forces, all these ratios, magnitude ratios have to be same. That means all these non-dimensional numbers have to be same. So therefore if we want to make the dimensional similarity, now come to the point, if you make to the dimensional similarity, then you have to keep all these non-dimensional numbers same while you do the experiments. That means you do the experiments, you say okay, if I have to make the dynamic similarity, I have to make the Reynolds number same. That means rho V d by mu same. Whether V is same, D is same, rho is same, mu is same, to that in the practice is not the factor, their combination has to be same. But who will tell you these numbers? Before that I tell you, after this, now when this is done, it is true that when we see that this is a group which has to be same for dynamic similarity, that means this group as a whole influence the problem. That means now one very interesting thing, the answer to the second query. If I now from my intuition feel that the performance parameter, for example the pressure drop in a pipe flow, in its dimensionless forms, that means if a problem governed by pressure force, viscous force and inertia force, if you find out the ratio of pressure force similar way by the inertia force, this is the concept actually, inertia force, you will get in the similar way delta P divided by rho V square, and this is known as Euler number. So therefore if we see that in our pipe flow problem which is governed by inertia force, viscous force and pressure force, so therefore I see that non-dimensional term, these are all dimensionless terms because this is the ratio of two forces. So therefore if by your interest you put all the dimensions of the variables, you will see they are dimensionless because they represent the ratio of the forces. So therefore we see that by our intuition, if the two dimensionless quantity govern the problem for dimensional similarity, so there may be a relationship between these two. That means these two has to be related with each other. That means this becomes a function of rho V L by mu. Then this is a beautiful thing. That means if delta P in its non-dimensional form or dimensionless form is a function of this non-dimensional group which contains all the independent variables or the controlling variables. So why not vary one of these which is very easy to vary? In the laboratory experiment it is very easy to vary velocity because difficult to vary the characteristic length which is the diameter of the pipe. So you have to purchase pipes of different diameters or fabricate pipes of different diameters. Mu and rho you have to seek for different fluids which is very difficult. So therefore it is very easy to flow velocity to vary because if you have a valve after the pump, if we change its opening, we can change the flow through the pipe. By varying the velocity V, we can predict the influence of this combined parameter which means indirectly the varying other parameters. That means if you make the velocity double means the same influence if you make the length double or if you make the viscosity half. That means if the group has a whole influence then is influencing parameter to this, I can change any variable and can find out the influence of other variables. Now the question comes, how do you know these parameters? So always you try to find out that what are the forces acting on it, what are the forces governing the parameters flow, and you write the representative magnitude and ratio. No, there is a simple way of finding out these dimensionless parameters which represent the dynamic similarity through the ratio of the representative forces that govern the flow in the two systems, and that particular theorem is known as, or the principle is known as, now I will tell you, Buckingham pi theorems. Buckingham's pi theorem, Buckingham pi theorem. Buckingham pi theorem. What is this? You all know these things. Buckingham pi theorem. Now I will tell you some tidbit concepts on. Now if a physical problem is described by m variables, if a physical problem is described by m variables, that means let us have m variables, that means let the variables are x1, x2, x3 dot 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 xm. Then we can write or we can express the physical problem as an implicit function of all these variables x3 dot 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 xm 0. If a physical problem is governed by m variables, physical variables like the pipe flow problem, velocity, diameter, viscosity, density, like that, and if all the variables can be expressed by n fundamental dimensions, that means all the variables can be expressed by n fundamental dimensions. For example, what are the fundamental dimensions? Mass, length, time, temperature. Now how many fundamental dimensions will be required to express all the variables depends upon the type of the variables. So if it is n, and if at the present moment we consider m is greater than n, I will discuss when m is less than n, m is greater than, m equals to n, what is the physical implication of it afterward. But we accept m minus n, m is greater than n, so m minus n is greater than 0. Then according to Buckingham pi theorem, this problem which is governed by m variables can be expressed as a function of m minus n term of dimensionless variable, which are grouping of these variables and known as pi term, pi 1, pi 2, pi 3 dot 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 pi m minus n 0. Again I tell you for your understanding, if a problem is expressed by m variables, and if m variables can be expressed by n fundamental dimensions according to this theorem, the problem can be expressed, or problem can be expressed in this way, or problem is governed by, rather why can be expressed, because it is governed by. If the problem is governed by m variables expressed by n fundamental dimension, then problem is in fact governed by m minus n dimensionless variables, which are grouping of this, all these dimensionless variables, which is expressed as pi 1, pi 2, this is known as pi term. That is m minus n pi terms. The problem then is governed by m minus n pi terms, means m minus n dimensionless terms, which are some grouping of all these parameters. What grouping then I will come afterwards, how to get that grouping. At least we can understand that the problem physics may be expressed by less number of variables if we express the variables not in terms of the dimensional variables, otherwise we require m variables. By the physics of the problem it is defined by m variables, but with the help of Buckingham's pi theorem we can show that this problem or the physics of this problem is actually governed by m minus n independent variables, independent m minus n independent dimensionless variable, independent dimensionless variable, and dimensionless variable. So number of variable is reduced in terms of dimensionless variables, and each dimensionless variable or term is known as pi term, and this there will be m minus n pi terms, and each pi term is the combination of the some combination of these problem variables. Okay. Now, with this I will tell you how to find out these pi terms. Okay. How to find out the pi terms. Now, my next question is that how to find out these pi terms. Let us first consider that the functional relationship is like this: x1, x2, x3 dot 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 xm is 0, and let n is the fundamental dimensions. Okay. N is the fundamental dimension. N is the fundamental dimension. Now, I know that there will be m minus n pi term. This is known by Buckingham's pi theorem. And how does it come? This comes from the dimensional homogeneity of the problem and established by the experiment. You can ask me, sir, how you get it? Buckingham's pi theorem is based on dimensional homogeneity problem, and while solving problem you will see that automatically it is understood. It is logically understood, derived because of the dimensional homogeneity, that m minus n pi terms. Now, how to find out all those pi terms? So, the method is like that, which is basically the Buckingham's pi theorem, which tells the method also. Now, amongst these m variables, we choose any arbitrary n number of variables. N is the fundamental dimension. Let us choose this first, this thing xn. Any arbitrary. There is no restriction that which n number of variables we choose. Any arbitrary n number of variables we choose. And then what we do? We write the pi term starting from the first pi term as the to the power a, x2 to the power a1, x2 to the power a2, x3 to the power a3 dot 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 xn to the power an, and with all these variables we club one variables which are not included in this variable, these n fundamental dimensions. So, n number of arbitrary variables are taken which are known as repeating variables. Why it is called repeating variables? This will be clear. These are known as repeating variables. So, there will be m minus n number of variables which are not taken as repeating variable. So, each and every variable we take x n plus 1 without any integer. This way we can form the pi terms. So, next pi terms is x1 a, x2 to the power a2, x3 to the power a3 dot 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 xn to the power an, xn plus 2, and all a1, a2, a3, an, and this a1, a2 from pi to pi term, they are different. The values of a1, a2, a3, a10, then this a1 may not be same, this a2, a2 may not be same. So, this way therefore, since we have to go m minus n automatically, the x n plus 1 to x m. So, that will make only m minus n term. So, m minus n pi term will be x1 to the power a1, x2 to the power a2, x3 to the power a3 dot 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 xn to the power n multiplied with xm, the last term. That means, if we take all the terms m minus n terms, we get m minus n pi term there. Now, what is done? I tell you that each pi term is dimensionless. Express this in terms of the fundamental dimensions. Let number of fundamental dimensions are n. We equate the indices of all n dimensions to 0, because this pi 1 term is 0. So, all fundamental dimensions indices will be 0, because ultimately these combinations in any pi term will be dimensionless. So, therefore, we get from each pi term n linear algebraic equations for a1, a2, a3, an, because indices of all these things will be 0 for all fundamental dimensions. So, this n linear algebraic equation for this n unknown, which are the indices, are found out for each and every pi term, and we get the pi term. That is all. Now, before I go to the next step to solve a problem, for example, I tell you the implication of m is equal to n. So far, we have considered that m is the number of variables and n is the number of fundamental dimensions, and m is greater than n. Now, there may be a situation, now you can ask me that m less than n, it is impossible. no physical process is being described by this, that number of physical variables describing the process is less than the fundamental dimensions expressing the variables, not possible. Another alternative is there, another situation, m is equal to n, then m minus n is 0, no pi term, no pi term. This indicates a situation that no process is being made. So, it is only an equilibrium situation. That means here m is equal to n implies the no process in the system. We are not interested in a static system, that means it is in equilibrium condition. So, only possible case of a physical system where the process takes place m greater than n. A situation may be there that m is equal to n plus 1. In that case m minus n is equal to 1, then only one pi term, that I will solve today. So, you will see only one pi term, but in most of the engineering problems m minus n is greater than 1 and number of pi terms are there. So, let me solve a very typical problem in this regard and very common problem in this regard. Let us see the problem first. Let us see the problem first. For a steady fully developed laminar flow through a duct, the pressure drop per unit length of the duct delta P by L is constant in the direction of flow, that you know already from the exact solutions that delta P by L for a fully developed flow is constant and depends on the average flow velocity V, the hydraulic diameter of the duct dH, that means in a pipe the hydraulic diameter is its diameter itself, the density rho and the viscosity mu of the fluid. Find out the pertinent dimensionless groups governing the problems by the use of the Buckingham's pi theorem. Let us translate this problem. Now, problem is very simple. Now, function of this problem test delta P by L. Delta P by L is a function of all these things. So, that means we can write function of delta P by L, the velocity, what are these? Then hydraulic diameter, then rho, then mu is 0. Actually, delta P by L is a function of, depends on this. I take all together to express a implicit functional relationship. This is the problem. Problem is defined by this implicit functional relationship, that delta P by L, velocity, hydraulic diameter, density and mu, functional relationship between them is 0. Now, before doing this problem, I tell you another rule, that while applying the pi theorem, two things have to be remembered, that repeating variables have to be taken at that number which equals to the number of fundamental dimensions. Any arbitrary number we can take. Number 2 is that condition, the repeating variable should not contain the output parameter or the performance parameter of the system. Third one is that all the repeating variables collectively must collectively contain all the fundamental dimensions. Again I am telling, the conditions for choosing the repeating variables are that the repeating variables, first is the number of repeating variables is the number of the fundamental dimension. No repeating variable should be a output or performance parameter of the system which you know from your physical concept, and all the repeating variables must collectively contain all the fundamental dimensions. Here the fundamental dimensions are m, L, T. So, now first m is equal to what? 1, 2, 3, 4, 5. What is n? m, L, T, n is 3. So, number of pi terms is what? Number of pi terms is 5 minus 3, 2. That means we have pi 1 and pi 2. Now, how to find pi 1, pi 2? Follow the process. So, here number is 3. That means any 3 variables we can take as the repeating variables. According to the condition, as I have told, we have to exclude this. We cannot take as this repeating variable. Our choice is between V, dH, rho, mu. So, but V, dH, rho, mu, any arbitrary 3 can be taken. Yes, there may be how many choice? 4 C3. 4 C3 means there may be 4 choices. What are those 4 choices? One is V, dH, rho. Another choice may be V, dH, mu, V, dH, mu. These are 4 choices, V, dH, rho, V, dH, mu, then dH, rho mu or V rho mu. So, these are the choices. So, what are the choices left to us? These are the choices. It does not matter, I have told that any arbitrary we can take these 3 as the repeating variable. Then incidentally we check that in these 3 all MLT there, in these 3 all MLT there, these 3 all MLT there, these 3 all. That means all these 3 combinations, these 4 combinations, the 4 combinations of these repeating variables are legally okay, are valid, justified. Any combination we can take. Let me take this combination V dH rho as the repeating variable, V dH rho as the repeating variable. Now, how to solve it? You see that it is very simple, nothing can be simpler than this. According to the problem, I know that I write, sorry, here you will not, here they can see, f is a function of delta p by L, V dH rho mu equals to 0. Now, I take V dH rho as the repeating variable. Our first term is that V to the power A dH to the power, let us do it with BC, rho to the power C into delta P by L. And second pi term is, obviously we have taken this, the left is mu, so V to the power A dH to the power B and rho to the power C and mu. Now, solve for ABC. First pi term gives, what is that? Pi 1 is equal to V is L t to the power minus 1 to the power A, L to the power B, M L to the power minus 3 to the power C. What is delta P by L? Delta P by L is M L to the power minus 3. If you say that, you have to remember this, the force is M L T to the power minus 2. So, pressure is L square. Again one is, that is L square M L T to the power minus 2, and again there is 1 L. That means M L to the power minus 1 T to the power minus 2.
L minus 2.
L to the power minus 2, because L 3 M L T to the power minus delta P divided by L square.
That is fine. So, M L minus 2 is fine.
Then it is L. So, L will cancel, M L to the power minus 2, sorry, L to the power minus. Then if we go for pi 1, you see that the in this is dimensionless. Let us equate the M dimension, C plus 1 is 0. Then L is minus A, plus A, sorry, L to the power A plus B minus 3C minus 2 is 0, and T minus A minus 2 is 0. If you solve here, it straight gives A is equal to minus 2, B is equal to minus 1, B is equal to 1, sorry, B is equal to 1, B is equal to 1 and C is equal to minus 1. So, A is equal to minus 2, B is equal to minus 1, A is equal to minus 2, B is equal to A here minus 2, B is equal to 1 and C is equal to minus 1. That means pi 1 becomes delta P by L divided by C is equal to minus 1 into dH divided by rho V square. So, therefore, my pi 1 term is determined. I put the value of ABC there. Clear? Now, pi 2 term, pi 2 is what? Pi 2, if you see the earlier one, pi 2 is this, pi 2 is this V A dH. Then again I write pi 2 is V to the power A dH to the power B rho to the power C into mu. Now, here also V is L T to the power minus 1 A, L to the power B, M L to the power minus 3 C, and mu is what? M L to the power minus 1 T to the power minus 1, this dimension you know T. And if we equate this M to 0, that is C plus 1 equals to 0, c plus 1 equals to 0. Then L, what is L? A plus B minus 3c minus 1 equals to 0. For t, the indices, sum of the indices 0 minus a, t here there is no t, minus 1 equals to 0. Now if you do it, you can solve it, a is equal to minus 1, you will get b is equal to minus 1, c is equal to minus 1, and the pi 2 becomes equal to mu by rho v dh. That means we can tell the problem can be defined by a function of 2 pi terms. According to Buckingham's pi theorem, it was 5 variables, but now it is reduced to 2 pi terms, pi 1 and pi 2. That means delta p by L dh I write first divided by rho v square. That means the number of variables in terms of its non-dimensional term, which represents the dynamic similarity, is reduced to 2. That means one can write other way, that dh delta p by L divided by rho v square becomes some function of mu by rho v dh. Now you know this is known, this is 1 upon Reynolds number, and this you will see afterwards is defined as the friction factor, that I will tell you tomorrow. This is defined as the friction factor in flow. So therefore this can be expressed as friction factor is some function of Reynolds number, different function, because it is 1 by Reynolds number. These are very conventional things. The Reynolds number you know conventionally, that is the rho v d by mu, that is the representative magnitude of inertia force to viscous force, and this is the friction factor. This definition, this clubbing is known as friction factor. So therefore you see that how we can just split into 2 pi terms. Now the question comes, sir, if we could have used other pi terms, other repeating variables, what could have been the result? It could have been different. Definitely if I show you the repeating variables, you can choose this repeating variable set, this set, this set. You could have landed with a different pi terms, but physically they are same and they are interdependent. That is the concept. Now I show you, you see the table, that this is explicitly given in my book, that if you take different repeating variables, you arrive at different pi term. If you see, I have done that these two repeating variables, I get these 2 pi term. Similarly, if we take these two repeating, this set of repeating variables, you get these 2 pi term. Functional relationship is like that. If we get these 3 repeating variables, then you get these 2 pi terms. And if you get these 3 repeating variables, you get different pi terms, but all the pi terms are interrelated. For example, if one takes this repeating variable, just a minute, if one takes this set of repeating variables, and if he is asked to prove that friction factor and Reynolds number are the pi term, then he does not land up to friction factor and Reynolds number. He may cry in an examination, I have done a mistake, so I have to start again or start with another set of repeating variables, so that I can land up to this value, because teacher has asked this, that prove that the 2 pi terms are like this, or friction factor is function of Reynolds number, where friction factor is defined like this, Reynolds number defined like this. But this poor boy has landed up to this pi term, another poor boy has landed up to this pi term. He does not have to do it again, because he must know that these 2 pi terms, if you make some combinations, you will land up to this. For example, if you make the reciprocal of this pi term becomes equal to this pi term. Again, if you make the division, this pi divided by this pi, that means pi 1 of set 2 divided by the pi 1, pi 2 of set 2 becomes the pi 1 of set 1. That means if we just see that any combination between the two terms if I make, I must land up to this. Similarly, if any combinations can be made between these two, you may land up this. That means all these functional relations or all these pi terms are interrelated. Number is same, 2. That means there will be only 2 independent pi terms. But if you have other 2 independent pi terms by choosing another set of repeating variables where this option is there, then you see that they are independent set. all these 4 are independent set. For example, here pi 1 by pi 2 of set 2 is equal to pi 1 of set 1, you see, and do it. 1 by pi 2 of set 2 is pi 2 of set 1. So, therefore, another important corollary comes regarding the pi theorem, that number of pi terms remaining the fixed, any combination of the pi 1 also gives it the same relation. For example, a physical problem is defined by this. Not altering this, one can tell that pi 1 by pi 2, 1 by pi 2 is the, it can be defined by this also. There is no difference between these two. Or pi 1 into pi 2, pi 2 to the power 1/3 is 0. All possible, that any combinations of the pi terms are possible provided the number of pi terms are same, and you do with these pi terms. Okay, so this is another rule. Now I tell you a very interesting problem. This is probably hardly done in any book, I do not know when. This situation arises that m minus n is 1. That means what happens? There is only one pi terms, m is 1 greater than n. The problem is like that, a free fall, when a body is falling freely, the vertical displacement of a body falling freely from the point of projection or the plane of projection at any instant of time depends upon the acceleration due to gravity, we know. That means this problem can be expressed functionally as the displacement from the point of projection, the time and the acceleration due to gravity is 0. So, how many? M is 3. What is n? N is 2, L and T. So, therefore, this is a case where pi is equal to 3 minus 2 is 1. Now, according to the condition of the pi terms, I have to choose two number of repeating variables. H is the output parameter, is a function of t and g, the displacement depends upon t and g. So, the only choice is Tg. So, our only pi term, I am not writing pi 1, pi 2, is nothing but according to the procedure of Buckingham pi theorem, g to the power b into h. And if you solve the thing in terms of this, t is t, t to the power l, g is l t to the power minus 2 to the power b, and h is l. And if you solve this, you will say that b is equal to minus 1 and a is equal to minus 2, which makes pi is equal to h by a is equal to minus 2, g, b is equal to, if you solve it, you will get that g t square is simply, you just solve for l and t, that a minus 2 b is 0, and for t l b plus 1 is 0, b minus 1 a minus 2, alright. So, therefore, you get it, that means the problem can be defined as a functional relationship of h by g t square is 0. That is, that we know the thing since our school days, h by g t square is half. This half comes from the theory of the subjects, either from experiments or by theory. This will be not told by the Buckingham's pi theorem, but Buckingham's pi theorem tells that this problem is defined by single pi term. That means, in this process h by g t square has a fixed value, and that is half. Okay, that is an example where there is only one pi term. The similar thing is done in my book, that same thing, the time period of a simple pendulum is a function of its effective length and the acceleration due to gravity, almost similar thing. So, therefore, we see the implication of Buckingham's pi theorem. Okay. How it is being implemented? Again, I just tell you in brief that Buckingham's pi theorem tells if a problem is defined by m number of physical variables by an implicit functional relationship of all physical variables, function of a x1, x2, x3, xm equal to 0, this problem can be expressed by a reduced number of non-dimensional variables. What are the number? If all these variables can be expressed by n fundamental dimensions, then these non-dimensional numbers are m minus n. That means, if the m variables can be expressed by n fundamental dimensions, the same problems can be defined in terms of the m minus n non-dimensional terms, pi terms. That means, the problem is governed by m minus n dimensionless terms, and these dimensionless terms are the clubbing of the terms. For example, delta p L dH, again I write, this is the concept, by rho v square ultimately becomes a function of rho v d by mu. That means the influence of all these parameters goes in a club, that means a group. That means they behave, they influence in a group. That means this group is a function of this group. That means they are expressed in terms of reduced number of dimensionless parameters, where each dimensionless parameters club or formed by the combination of the dimensional parameters. The restriction, now the process of Buckingham's pi theorem is choose the number repeating variables whose number is equal to the number of fundamental dimensions, and the conditions are that the repeating variable should not contain any output performance parameter, output or performance parameter. The repeating variables as a whole all together must contain all the fundamental dimensions. Okay. So, these are the conditions of the repeating variables, choice of repeating variables. There may be a number of choice of repeating variables. As I have told, when m minus n is greater than 1, there may be number of choices of repeating variable, number of sets are there, number of sets of n such repeating variables. Any set is same, you take any set and land up with the pi terms, and if you get different, take different sets, then the pi terms, number of pi terms remain same, but pi terms may be different, but they are all interdependent. Okay. So, this is in brief this thing. Now, before closing, I will tell you there is another method of dimensional analysis. This also evolves from the dimensional homogeneity, that is known as Rayleigh's, anything is left? Rayleigh's indicial method. Rayleigh's indicial method, whether I capital de do, method. What is that? Like Buckingham's pi theorem, Rayleigh also introduced another method, indicial method. What is that? Let us better explain through a problem, then you will. Now, the pi flow problem, we express in the Buckingham pi theorem that delta p by L v dH rho mu 0. Then what we did? We took any 3 out of these 4, because this is the output parameter as the repeating variables, and formed 2 pi terms equating the indices of the fundamental dimensions to 0. We found out the indices and found out the pi term. But in Rayleigh's one, Rayleigh's expression is that we express the Rayleigh's indicial method, the output parameter, in this way: some constant a into v to the power a, okay, v to the power a, dH to the power b, dH to the power b, rho to the power c, and mu to the power d, unknown exponents. It is almost similar, but a little different. This I do not know which one will appear to you very simple. This is like this, but Buckingham's theorem is relatively simple as I understand. Then what is done? You just put the dimension in both the sides. What is delta p by L? M L to the power minus 2 t to the power minus 2. Okay, what is delta p by L? M L t to the power minus 2 is the force, then L square into L, M L to the power minus 2 t to the power minus 2, and that becomes equal to A. V is L t to the power minus 1 to the power A. This is dH L to the power B. Rho is M L to the power minus 3 whole to the power C. Then M L to the power minus 1 t to the power minus 1 to the power D. Now, here if you just equate these dimensions in both the sides of M, L and T, you get an equation like this. Equating the indices of M, L and T on both the sides, you get, this is very simple, C plus D equals to 1. Then next one, A plus B, you check it, minus 3C minus D equals to minus 2. This A plus B, this is L. C plus D comes from M, equating the dimension of M is 1, L is minus 2, and equating the indices of T, we get A minus D, T is minus A minus D, is equal to minus 2. Now, here one thing, there are 4 unknowns. Difference is that there are 4 unknowns but 3 equations, because fundamental dimensions are 3. But why there are 4 unknowns? We have taken the parameters like that, all parameters 1, 2, 3, 4. There is no repeating variables of 3, number 3. So, therefore, 4 unknowns, 3 equations. So, therefore, we can eliminate 3. We may not solve for A, B, C, D, but we can eliminate 3. That means, we can express these 4 unknowns in terms of 1. If we do that, for example, A, B, C in terms of D, then you get A is equal to 2 minus D, B is equal to minus D minus 1, E is equal to 1 minus D. And if you put all in terms of this D, that here V to the power 2 minus D, DH, this B is minus D minus 1, DH, then rho is also 1 minus D and mu D, then what you get is that you get, if you put that, then what you get? You get this one. If you do that, then you will get delta P by L is A into V to the power 2 minus D, because A is 2 minus D, B is minus D minus 1, very simple, C is 1 minus D and mu is D. And if you take all these together, indices together, now what it is? A into, that is V square, then this is divided by V square rho by DH. So, delta P by L, A V square rho by DH, and then all D will come, that means mu by, with indices D, that is V, that is D, that is rho, that means rho V DH to the power D. That means this is the relationship that, now if we take it here, then DH delta P by L, DH delta P by L rho V square is A into, then this also gives the same thing. From dimensional similarity, since this is non-dimensional, these two combinedly will be, that means this non-dimensional term is constant into this. That means this tell that ultimately the problem is defined by this non-dimensional term and this. That means this is pi 1 as our from Buckingham pi theorem, this is pi 2. But the value of A and D will be found from the experiments or theory of the particular problem. Buckingham's pi theorem will never tell the explicit relationship, only they tell the implicit relationship. They only tell the number of pi terms and what should be the pi terms, what should be the clubbing or the grouping of the terms to define the pi terms, reduced number which define the problem. But any explicit relation, here explicitly it is expressed in terms of a constant to the power and indices, but this proves that the clubbing is like that. That means by the dimensional homogeneity, it is found that the dimensional variables are clubbed like that, flocking together, flocculation type of thing. They are coming together, and form the pi term. This is the Rayleigh's indicial method. It is almost similar to Buckingham's pi theorem, but a little different. There also we can recognize that a reduced number of non-dimensional terms as the pi terms that define the problem. Clear? So, I think about dimensional analysis we do not have to say anything more. Is there anything more? Which?
3-4 questions.
No, questions I will take 3-4, but is there anything more that they should know conceptually? So, important things, because this is the most simple thing as far as we do it or execute it, but concept is very important. So, be careful about the concept. I am now highlighting the concepts which are not usually found in many books, that first of all the physics of the process has to be same. This is very important. I give you an example why, that while modeling the thing, that in the experiment by reducing the geometrical size, sometimes the physics may be changed. A very interesting thing I am telling you. You may tell, sir, who will go to find out the physical similarity between a pipe flow and the free surface flow? Correct. But for example, you are simulating a vertical flow through a vertical pipe. but you think that the simulation I will make a very small capillary pipe whose length to diameter ratio is same, but reducing that size may change your physics. The capillary force will be dominant in your flow, which was not there in the actual system. Understand? Similarly, if you make a river model, a very shallow, by a shallow tank, then what will happen? The turbulence effect in the river may be died down in the shallow tank, so that the physics may change. If you want to predict the behavior of a ship, power requirement of a ship by towing a ship in a tank. So, therefore, sometimes it is important, why I am telling that physics of the problem should be same, that it is important sometime in scaling this system, you must be very careful always that the physics should not be distorted or should not be changed. So, physics has to be changed, then kinematic similarity, geometric similarity, kinematic similarity and dynamic similarity, all three have to be maintained, and the requirement is that we have to keep the dimensionless parameters same for this similarity to be maintained. Where from we will get this? Either from Buckingham's pi theorem or from Rayleigh's indicial method, either of the two. So, these two processes have been elaborately told. The Buckingham's pi theorem, the conditions of choosing the repeating variables is very important. In Buckingham's pi theorem, always m is greater than a number of physical variables has to be greater than the number of fundamental dimensions expressing the physical variable. Otherwise, there will be no process, or m minus n is 0, there will be a equilibrium. And when m minus n greater than 1, number of choices for repeating variables are there, because there will be an arbitrary set, but any set if you take, you will end up with the pi terms which are interdependent. Alright, these are the tidbits, and I think I can end here with all sorts of concepts in the physical similarity and dimensional analysis. We can take 1 or 2 questions before lunch, because I think this is very simple, questions will be less, however, we will take. 1073. 1073.
Good morning, sir.
Good morning, please. Good morning.
Sir, for internal analysis,
Uh,
for example, external flow, sir, internal analysis, external flow over aerofoil, what are the model laws regards to verification?
what is the?
Model laws, that is, what are the Reynolds number or Probe number? These are the things we got to make it similar.
Okay, yes, to make it similar, I tell you what should be the Reynolds number and Froude number range. Of course, in a aerofoil, Froude number does not come into picture much, it is the Reynolds number, it is other numbers will come, Cauchy number. However, any dimensionless number, for example, Reynolds number, in which range you will do the experiments depends upon the range of Reynolds number in practice. The concept is like that I do the experiments in my laboratory. You see, always any empirical results or empirical equations is valid within the range of experiments. So, I may change the variables, but the range of the non-dimensional variables have to be same. That depends upon the situation in the practice. I cannot tell you the value quantitatively now. So, you are predicting the, for example, the pressure drop over a aerofoil in practice. So, you have to know that what is the Reynolds number encountered in practice, the range of Reynolds number. You have to do the experiments with that range of Reynolds number. So, your alteration of the physical variable must ensure that range of Reynolds number. You understand? So, that depends upon the problem. Actual problem in practice, you have to get the data. That is the data information, that is not your concept. You clear your concept first. Okay. So, what Reynolds number range you will make the model experiments, that depends upon your data from the field. You understand me? Okay.
Thank you, sir.
Okay. अच्छा दाओ.
Hello.
Hello, yes.
Good afternoon, sir.
Good afternoon.
Hello.
Hello, please.
Good afternoon, sir. My question is related to boundary layer approximation.
No, No, second half the questions will be answered in boundary layer approximation. Here only
Good
dimensional
afternoon,
analysis.
sir.
Yes. In second half it will be
The
answered.
question is related to boundary layer approximation. Can I continue?
This will be answered in the second half. Today I am not teaching boundary layer approximation. What is your question? Let me
Hello.
hear. Yes, what is your question? Boundary
Good
layer.
afternoon, sir.
Huh?
The question is related to boundary layer approximation.
রাখবে কেটে দাও
1330
1330
Hello, good morning, sir.
yes
So, when we found two independent dimensional terms, delta p dh by l rho v square and mu by v dh and rho. So, whatever that numerical value a and d.
A and D I told that A and D the functional relationship have to be found from experiments. Buckingham's pi theorem or Rayleigh's indicial method will not tell about any functional relationship. It is the way it is expressed in Rayleigh's indicial method by A and D. We are not bothered about A and D, that has to be found from experiment. Only you know the variables in the grouping form from the Rayleigh's indicial method. Okay, A and D will be found from experiments.
So,
Okay.
it is not derivable, sir.
No, this is not derivable from Rayleigh's indicial method, it is derivable from other theory or from experiments, definitely derivable. Exact solutions you make Navier-Stokes equation, laminar flow derivable, but Buckingham's pi theorem and Rayleigh's indicial method only give you, try to understand what it is being taught, that grouping of this thing I am telling 100 times. The Rayleigh's indicial method, Buckingham's pi theorem, they tell you the number of the pi terms and what should be the pi terms, what grouping of the variables, dimensional variables will be pi term. But what is the explicit functional relationship between the pi terms, that is not in the domain of Buckingham's pi theorem and Rayleigh's indicial method. This can definitely be found out from theory, but theory relating to that field. Okay, by the solution of Navier-Stokes equation, by the solution of other problem conservation equation or from experiment. That is altogether different. We are not interested about that value. We know for a free fall of a body h by gt square assumes a fixed value. That is the information given by that. Whether h by gt square will be half or something else, that will be found from experiment or very elementary classical mechanics derivation. Okay. So simple thing I am telling again. 1108.
Good afternoon, sir.
Yes.
Hello.
Yes,
Good
please,
afternoon, sir.
please tell.
Sir, my two questions are there.
Yes.
The first question is that what is the basic idea behind the dimensionless?
I told several
There are
times.
two questions are there.
Next,
First question.
next.
Next is that once we converted the physical phenomena, into mathematical formulation
Yes.
with the some conditions, boundary condition, initial conditions, and how to convert that problem to the dimensionless variable. Is there any particular way, particular method?
See, again you probably have not understood what I have taught. I am sorry. First question is that, what was your first question? What was your first question? Do you remember? Huh?
What is the basic?
Basics of the dimensional analysis is the dimensional homogeneity. It is based on the dimensional homogeneity, this dimensional analysis comes, that you can reduce the number of physical variables to a lesser number of non-dimensional variables. Okay? And boundary conditions, initial condition, it is irrelevant here. We are not going for any theoretical analysis based on conservation equations like Navier-Stokes equation, Bernoulli's equation, Euler's equation. Try to understand, these principles tell you what should be the number of non-dimensional terms defining a problem, which is reduced. Try to understand the beauty of the problem. If a problem is defined by m number of physical variables, this can be reduced by m minus n number of physical variables. Don't you understand this? If a pipe flow problem is governed by Reynolds number rho Vd by mu instead of separately rho v d mu, then we can vary the velocity v and can express the influence of d, mu, everything. So, how important is this concept that the group itself as a whole influence on the pressure drop in that non-dimensional term. Okay, that is the beauty of this thing. It does not solve for any other thing, that explicit functional relationship, initial condition, boundary condition, this does not come. Try to appreciate the problem. I started from the beginning that when you do the experiments in laboratory, you have to make these numbers same with corresponding to the actual situation. Try to understand. So, your other variables may vary, but this thing has to remain constant. This is the number one advantage. I started at the beginning that totally integrate my lecture from the last to the beginning. And second is that when we know that a particular group collectively influence the output parameter, then I may vary only one parameter of the group which is easiest for me to vary. Then I can explain the